Hello and welcome back. We are starting our 14th lecture. We have been discussing the Newton's method of using divided differences to compute the interpolating polynomials which interpolate a given function on distinct n plus 1 points x0, x1, so on up to xn. And now we continue with this discussion. Let me just quickly recall for you that whenever you have this polynomial Pn, which interpolates this given function f on these n plus 1 nodes, which are x0, x1 up to xn, then we define the Newton's divided difference f of x0, x1 up to xn. Sometimes we will not write x1 there. The three dots that are given, they simply mean that we will continue from 0 to n. All the in between nodes are assumed. So this divided difference is the coefficient of x power n in the polynomial Pn. That's our definition of this divided difference. And we also have a formula for writing Pn in terms of this divided difference and Pn minus 1. So there is a recursive way to define or to compute these interpolating polynomials using the divided differences. And for the divided differences themselves, we have a formula. So these are some of the interesting things. We have also noted that the divided difference f of x naught dot 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 up to xn does not really depend on the ordering. Whichever way you order your nodes, the coefficient of x power n in that polynomial Pn is going to be the same. So that's some nice thing about it, and we will study some of these properties of the divided differences. So there is this nice table which we have to compute the divided differences. So once we have this first row of x0 up to xn, then we simply have their polynomials f of x0, the value of these function f at x1, x0, x1, x2 and so on. So these are the constant polynomials which interpolate your given function on those singleton nodes. And those are also defined to be our Newton divided difference at that singleton. So f square bracket xi is simply the function value on the node xi. And then we can inductively compute these divided differences. For instance, f x naught x1, this is f of x1 minus f of x naught, x1 minus x naught. Okay, so what you do is that you extend this triangle, look at the endpoints, look at the first, look at the endpoints, those are the nodes which you are going to use, and the divided differences that you get by going down by one level. For instance, so I told you how to compute f of x naught x1, which will be f of x1 minus fx naught upon x1 minus x naught, or it can be f of x naught minus fx1 upon x naught minus x1. If you go to this divided difference f x naught x1 x2, then you extend from this point a triangle. It is going to, the one level lower divided differences are these f of x naught x1 and f x1 x2. Then our formula to compute f of x naught x1 x2 will be that you look at x naught x1 minus this value x1 x2 and divide it by x naught minus x2. Or you can do it the other way. So you will have f of x1 x2 minus f of x naught x1 upon x2 minus x naught. Whenever you are looking at, so for instance, if I look at this f of the final formula, which is x naught x1 up to xn, the final divided difference, and I extend the triangle, it will encompass the whole table. But you go to the previous ones, that would be f of x naught x1 x2 up to xn minus 1, and below that you would have x1 x2 up to xn. So you are going to take the difference of these two upon the difference of the points, the nodes x0 and xn in the correct order. If you are putting the f of x0 x1 up to xn minus 1 before, and then you subtract the next one f of x1 up to xn from this 0 to n minus 1, then the denominator will be x0 minus xn. Or here if you put it the other way, then these are also the other way. So you all you need to do is to perhaps write this table for say n equal to 3 or n equal to 4 to understand how this is to be done. But then this is really a very effective way of doing the calculations. And I also told you that everything is independent of the order of the points. So we can compute the polynomials Pn in the forward way as well as the backward way. To compute the polynomials, you can go across any path. So all you need to do is that from the first order divided difference, which will be f of x naught, f of x1, f of x2 up to f of xn, you start from them, you go to the second order divided difference, then the next order, then the next order, and so on in any way. In particular, we are going to tell you two such ways, the forward and the backward, and those formulae we will write down for you. So for instance, I'm again writing the same table and I have written some entries in the blue color. And the blue color means that I'm going to be I'm going to use um, these blue entries to write my polynomial, the Lagrange polynomial. And the way to write that would be this, that I start from f of x naught, then I go to f of x naught x1, and to that I multiply by the linear polynomial x minus x naught. And then I take the next level divided difference, which is f of x naught x1 x2, and I multiply by the degree 2 polynomial, which is the product of x minus x naught x minus x1, and we continue this way. So this is going in the forward way. You may also go backward way, which is that you are going from xn to xn minus 1 to xn minus 2, and then in the end you will reach x naught. And then the formula for the Lagrange polynomial is f of xn plus the divided difference f of xn minus 1 xn, which is the one level up. And then you are now going to multiply by the linear factor x minus xn, which corresponded to the point you just had before you. Then you go to the next level and multiply to that by 2 degree 1 factors corresponded to the previous ones. So this way you can just go along any path and you will get the same Lagrange polynomial. So we will do an example. As usual, the examples which are done in the lectures are easy examples, and the point of doing it is that there are no any mishaps during the lecture. So this example in particular is rather easy, but we will have not very difficult examples in our tutorials and also in the examinations. We have several exams. So suppose I look at this function f, whose values on 0, 1, 2 are given to be 1, 4, and 15. And I want to find the polynomial, which will now be a polynomial of degree 2. There are 3 distinct nodes and the values are such that linear polynomial seems to be difficult. So it will be a polynomial of degree 2 and we want to compute this. So we want to compute the table. This table is given to us because 0, 1, 2, these are the 3 nodes that we have. 1, 4, 15, these are the values. Okay. So this is f of x naught, this is f of x1, this is f of x2. This is the divided difference f x naught x1, which is obtained by taking 4 minus 1 upon 1 minus 0. Or you may think of it as 1 minus 4 upon 0 minus 1. You are going to get the same number. And 11 is obtained by looking at 15 minus 4 upon 2 minus 1. Okay. And then finally 4 is obtained by, I told you that you start this triangle from this point and it hits 3 and 11. You take the difference of 3 and 11 in some order and then divide to that by the difference of the nodes. So if you take 11 minus 3, that would be 8. You have to divide to that by 2 minus 0, which gives you the value to be 4. This is the table. And now we are going to use the forward values from that to compute our degree 2 interpolating Lagrange polynomial. So P2x, once again it will be f of x naught, which is just 1, plus 3 into f3, which is f of x naught x1, and you have to multiply to this divided difference by the linear polynomial x minus x naught, but x naught is 0. So it would simply be plus 3x. Okay, and then the next one would be 4 into x minus 0, x minus 1. So that gives you 4x into x minus 1. And then you can just compute this polynomial, which turns out to be 4x squared minus x plus 1. The backward table, it's the same table. We will be taking the backward values. So here the polynomial will be 15 plus 11 into x minus 2, because we are taking the backward values. The first divided difference is f of x2. So this will be 11 into x minus 2, and then it will be 4 into x minus 2, x minus 1. And you can again compute, the value has to be the same polynomial, and it is indeed 4x squared minus x plus 1. So both the backward and forward way will give you the same thing. You could have also done it by looking at f of x1 here first, 4, and then you would go to f of x1 x0. So it would be 4 plus 3 into x minus 1 plus 4 into x minus 1 x minus 0. That would give you the same polynomial again. So there are many ways to obtain the Lagrange polynomial from the divided differences due to Newton. Okay, for computation of these polynomials, the nested forms are also useful. So this is, for instance, if you were using the forward formula, then forward formula is given in the following way. You have the zeroth order divided difference f of x naught plus the first order divided difference x naught x1, and then you multiply by the linear factor. Then second order divided difference, and you are multiplying by degree 2 polynomial, and so on. So we notice that once you have written this zeroth order divided difference, in all the other terms, x minus x naught is a common factor. So we indeed do it that way. You write the zeroth order divided difference f of x naught, and to that we add the x minus x naught. We take it as a common factor outside, and then you have several terms inside. So out of them, the first one will be f of x naught x1, the first order divided difference. This is now a constant term. Once you have taken the x minus x naught term out, then this is the constant term of the factor polynomial. To that, we will multiply by x minus x1, because once you have taken x minus x naught out and you have taken care of this x naught x1, now these two terms have been taken out, and in the remaining n plus 1 minus 2, so n minus 1 terms, x minus 1 is common. So you again take x minus 1 common, x minus x1 common, and you write the remaining terms. So this is the way to write the nested form of the polynomial, and this is extremely useful in computing. In particular, if you were to look at P2, the one that we have computed in our example, it would be f of x naught plus x minus x naught into f of x naught x1 plus x minus x1, the next order divided difference, and then you simply complete the bracket. So what we could have done would have been f of 0 plus x into f of 0 1, x minus 1, f of 0 1 2. That is all. If you go one step higher, P3 would be f of x naught plus x minus x naught into the constant term is the first order divided difference f of x naught x1 plus x minus x1 into the second order divided difference f of x naught x1 x2 plus x minus x2 into the last third order divided difference, and then we have to complete the blue bracket and then the magenta bracket. So this is the way we would write the polynomial P3 in the nested form. One thing about nested form is that is something that we have already seen, that this nested form is very effective for computation. It reduces the products by quite a nice factor, almost half. It reduces the thing by a factor of 2. So doing the computation for these Lagrange polynomials using divided difference due to Newton and using the nested polynomial format is very effective in computing the Lagrange polynomials. Okay, so now we get a bit greedy and we would like to use these divided differences and see whether we can write a function. We can use a function. We can use these divided differences to write down a function. So for that we note, first of all, that whenever we divided these, whenever we defined these divided differences, we needed that these nodes be all distinct, because if you don't have distinct nodes, then we don't have Lagrange polynomials interpolating these uh, functions, right? So the nodes have to be distinct. In the original form of Lagrange polynomials, we needed to divide by x naught the differences of these xi's from xj's. So these xi and xj have to be different. Uh, Otherwise there is no solution for that. You know what can happen is that whenever you have these same nodes and if the functions themselves are taking different values, then we have a contradiction. Then we don't even have a function. Whereas if you have the same nodes and the functions are taking same values, then you will ignore the multiplicity of the nodes and take the node appearing only once. So this is what we will do. And therefore this divided difference, which is taken from the x power n coefficient, that really doesn't exist because the number of nodes has now gone down. So the fact that the nodes be all distinct is very much important when we used our definition to write down the divided differences. But in fact, we are now going to think about how the definition can be modified to see where the sum of the nodes can also be equal. So before going to that, let's observe that the mean value theorem will tell you that f of x naught x1 is the derivative of your function f at some point xi between x naught and x1. Okay, so we will, whenever we make a statement like this, we will assume that our function is continuously differentiable and so on. All right, so don't get confused about those terms. Don't think what would happen if your function is not continuously differentiable. Then we don't have equality. That is straightforward. But whenever we are writing down the equality, we are assuming that such things hold. All right. So how does this hold? This is because the left hand side f of x naught x1 is fx naught minus fx1 upon x naught minus x1. And then the mean value theorem will tell you that this difference upon the difference is equal to derivative of the function value at some point between x naught and x1. And in fact, you have a general such statement. What we have is that whenever you have x naught, x2 up to xn, and you have your function to be n times continuously differentiable, now I have to mention that because I'm stating a theorem, then this divided difference value is equal to the nth derivative of the function at some point between a b. So the divided difference is not something which is randomly cooked, but it is related to the function in this very, very nice way. So now this will tell you what the function values have to be, what the divided difference has to be if you allow some of these nodes to be equal. So let's again start from the basic step, which is the two nodes, x naught and x1. Now x naught and x1, whenever you have these two nodes, then mean value theorem once again gives you that the value of that divided difference is f prime of some xi between x naught and x1. So if you take x naught and x1 to be the same, what is the possibility for xi? Xi cannot be anything else but be equal to x naught, and which is also equal to x1. So we will we take inspiration from this mean value theorem and define the Newton's divided difference of order 1 f x naught comma x naught to be the derivative of the function f at x naught. This is our definition. And what is the reason for giving this definition? Because we have noticed that the mean value theorem tells you that whenever x naught and x1 are distinct, then the first order divided difference of due to Newton is equal to the derivative at some point between x naught and x1. And this is what inspires us to give the definition of the Newton's divided difference whenever the two nodes are the same. Okay, we go one step higher. First of all, okay, so this gives the equality because if you are computing f of x naught comma x1 and then you are letting x1 go to x naught, the f of x naught comma x1 is really f of x naught minus x1 upon x naught minus x1, and if you are taking the limit x1 going to x naught, that is really the derivative by very definition of the derivative of the function at x naught. So we get the equality of this continuity of the function f of x naught comma x, but we will come to that later. We are going to now define this x naught up to xn in the similar way whenever the nodes are not necessarily distinct by taking limits. And what do I mean by this? For instance, if we are looking at x naught, x1, x naught, we can permute the entries because the order of the entries is not important. So it is x naught, x naught, x1, and then we use our formula that this is x naught, x1, which is the second and the third node here, minus the first two nodes upon x1 minus x naught. That is our formula for computing the divided differences. But here x naught is really the derivative at x naught. So this is equal to f of x naught comma x1 minus f prime x naught upon x1 x naught. So here we have used the limiting because x naught comma x naught is given by our limiting process f prime at x naught. Okay. So this is when we have two of the three equal. If you have all three to be the same, then it's not really a very difficult thing to imagine that it would then be the second derivative of x naught divided by 2, because we had the general form of the mean value theorem. The mean value theorem gave us this line, which is the very first line in our slide. But whenever you had x naught, x1, x2, that has to be the second derivative at some point xi upon 2 factorial. And so if you are going to take x naught equal to x1 to be x2, then that xi has to be x naught. And so once again, f of x naught, x naught, x naught is the second derivative at x naught divided by 2. So this is the way we are going to define these divided differences whenever the nodes may or may not be the same. All right, so this f x naught, x1, x2, xn has been defined in general. So earlier, our constraint was that whenever you had x naught, x2, x1 up to xn minus 1, the last node xn was not allowed to be any random number, but it was something which is not equal to the first n minus 1, first n nodes. But now we have allowed the last one to be any real number. It can be equal to some of these or it can be any other real number. So by letting this last xn to be as a variable, we have indeed obtained a function of the variable x. What does this function tell you? It is f of x naught, x1, comma, dot, 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 comma, xn minus 1, because the only last one, xn, is called x. Up to xn minus 1, we have our nodes, comma, x. So this is the function. Once you had these n minus 1 nodes, then for any x, we have a function value given by this Newton's divided difference f of x naught, x1 up to xn minus 1, comma, x. This is our function. This function is continuous. In fact, if you were looking at only x naught comma x, whenever x is not equal to x naught, the formula will be the usual Newton's divided difference, which will be fx minus x, f of x naught upon x minus x naught. But whenever x is x naught, we have defined, remember, we have defined f of x naught comma x naught to be the derivative at x naught. And because we are assuming all nice properties of on our function, we see that the limiting value of the first formula is equal to the second value, and therefore this function is continuous. And in general, we will have f of x naught up to xn minus 2, xn minus 1 x equal to, so I will flip the x and xn minus 1, and we get this recursive formula. Remember, we have this recursive formula for the Newton's divided differences. So this recursive formula will tell you that I have a continuous function here already. I subtract another continuous function from that and I divide by a real number. So by induction we will have that the first the x1 xn minus 2 x that's a real continued function, that is a continuous function, and here you have a continuous function, and then we are simply dividing by this real number xn minus 1 minus x naught. So we do get continuity. You have to be, of course, careful, because some of these x1 x2 up to xn minus 1 may happen to be same. So for instance, if you were looking at x naught, if you had x naught equal to xn minus 1, then we will have to replace xn minus 1 with something else. And if all of these are happening, all these happen to be same, then we will have to just work with x. And then of course, at the end, we will have to use the limiting formula. So with this, we are going to stop, because this is what we have for the Newton's divided differences. We will see whether we can say something more about this. There was some small remark that I wanted to make, which is that Lagrange was the one who gave this interpolation formula, and typically, between France and Britain, there is this tussle of who does better. And Lagrange, who comes from France, he gave this formula for the interpolation of the function on n plus 1 distinct nodes. And it's interesting that Newton came, because Lagrange's formula was very difficult to improve upon. But then Newton from Britain, he came and he gave this definition of divided differences. You will see that there are these old books which talk a lot about divided differences. That's because before the computers came up, today we have computers, and so computing Lagrange polynomials is not really difficult. If you write down a formula, then you don't care whether you use forward differences or backward differences. Any such formula, or you can just compute those Lagrange polynomials, and using those Lagrange polynomials, you have the polynomials Pn. Once you have computers, then your speed has gone up by quite a fold. Whereas earlier, it was not possible to do, because you did not have computers with you. And therefore, Newton's method of using these forward and backward differences was a very useful tool. So even to this day, this continues, as is very clear from the example of the Fermat's last theorem. If some of you are interested in seeing this history of some of these very interesting problems, tussles between two countries, two neighboring countries, then you can go and read more on this on the internet. So we will stop here at this moment, and we will continue with our next lecture. Thank you very much.